Okay. So far we have seen a PN junction bipolar transistor where the field was created by the junction, and the amount of field, when we modified the field, the current flowed. So that is fine as far as the PN junction is concerned or bipolar is concerned. Now we're going to study about a new kind of device which is called the metal oxide semiconductor device, where the field is now created from across an oxide, just like in a capacitor. So the field is not created across a junction, but across a insulating material, which is this oxide, right? And we'll start studying the capacitor property of this term of this device first, because this gives a very good understanding of what happens in this device, how it works. Then we will expand it to a transistor, which then becomes a MOS transistor. So let's assume that you have a semiconductor, piece of semiconductor, silicon in this case, and you dope it with p-type acceptor atoms. Okay. Acceptor atoms, as you know, creates a lot of free holes. There are of course some electrons, free electrons as well, but their numbers are fairly small. Okay. This body is called the substrate, or is called the bulk, because on this device only the other kind of devices are grown. Okay. On top of it, let's assume that we put an oxide, a small thin layer of oxide, okay, through which we'll create a field later. Okay. On top of it, we put a material called the gate. It's either a metal or it's a heavily doped polysilicon crystal. Okay. This is called a gate because this controls what happens in the substrate, and we'll see that why it's called a gate later. Now, let's say we bias the gate related to the substrate, and with this bias we call it VGB. When VGB is less than 0, that means the gate is lower potential than the substrate, then you know that the holes will get attracted towards the surface. The holes will get attracted towards the negative side. And you see that it tends to accumulate on the surface. And the electrons will get repelled away from it. These repelled electrons will then accumulate onto the gate. It goes through the battery and then gets accumulated on the gate. So now we can see that there is an excess electrons here, there's an excess hole here, and this looks exactly like a parallel plate capacitor. Okay. These are all mobile charges here, and these are also mobile charges, and separated by an oxide, which is, let's say, T-ox thick. Then you get a capacitance across these two points. Okay. You got a field first from the H to from the positive side to the negative side, which means there's a voltage drop. Okay. And this, as I said before, exactly like a capacitance. Two terminals of a capacitance, the poly here and the substrate with the excess holes here. So since there's a lot of excess holes here, the conductivity is very good at the surface. Right? So these are the two plates of the capacitance. Of course, the gate is connected directly to this, and this portion of the substrate where there are a lot of holes is connected to the p-type, to this terminal, through the substrate. The substrate is also fairly doped. Remember, at the interface between the oxide and the substrate, there are a lot more holes because they have been attracted by the field. Let the charge on the poly or the gate is QG, Q gate, and charge on the surface is QB. Then QG plus QB has to be 0 because whatever went from here went out there. Right? Capacitance is nothing but we'll define capacitance as the change in the amount of gate charge to the change in the VGB voltage. Okay? Because that is capacitance. We've seen that in the PN junction as well. Just the change of charge relative to the change in voltage has got the capacitance. Actually, if it is linear, then you can call it capacitance, otherwise called incremental capacitance, but it doesn't matter. We'll just call it capacitance for a moment. Okay. So you plot CGB versus VGB. Since at negative voltages, there's a number of holes that get collected here. You'll expect that to be just Cox and flat, right? As you reduce VGB, more holes will go here and more electrons will accumulate here. The capacitance, the ratio of the charge to the voltage remains constant, and that value is called Cox, which is just determined by the cross-sectional area as well as the thickness of the oxide and the type of oxide. It's epsilon naught A by D, right? So per unit area is epsilon naught by D, where D is the oxide thickness here. Now, let's say instead of getting it negative, the same circuit, same type of material which is doped p-type, and the gate here with the oxide is now biased with greater than 0 voltage. Okay? That means you bias the gate higher potential than the p-type. When it is doing that, you will actually attract the electrons to this side, which are the minority carriers anyway, and the holes will get repelled away. What this does is that if some of the holes then will go up here, and what it does is, because the holes are the majority carriers and they left the atoms from here, you will get kind of a depletion region here near the surface. If an atom from which a hole has been taken out assumes a negative charge, so you see that, and they are immobile. They cannot conduct electricity, but they give you a charge. The charged atoms, negatively charged atoms sitting out here. Okay? This is the depletion region, just exactly same as we saw in the PN junction, except that the field is not coming from a junction, but it's applied through the oxide. Now, if you increase the voltage further, more holes will go here and more depletion charge will be uncovered here. Okay? Exactly like in the PN junction. Okay? So it's similar. So this is also like a capacitor where the gate has a charge Qg, and the charge on the other side now is the Q depletion charge. Okay? There are a few electrons here, but that's since it's minority carrier, it didn't matter so much. There's going to be a whole lot of depletion region charge. Okay? So Qg has to be equal to Q dep. Of course, with the negative sign, which I've let's assume it's mod. Qg plus Q dep is 0. So Qg actually is modulus of Qg is equal to modulus of Q depletion. Okay. And CGB, as we defined before, is nothing but the dou QGB, the variation of Qg versus variation of VGB, and that happens to be variation of Q depletion by variation of VGB. Because there's a negative sign, but that will get taken care of in the derivative. Okay. And we know that this is nothing but the depletion region capacitance, and that is actually proportional to 1 by square root of the voltage applied across the junction, or in this case across the oxide. Right? So the capacitance starts to fall. Right? Starts to fall because it's only the depletion region which causes the capacitance. And you see that's 1 by square root of V. As V increases, square root of V increases, so 1 by square root of V reduces. It just reduces here. Okay. Hope that's clear. Now, what happens if you increase the voltage even higher? So that is the gate, you take it even higher now. Right? At some point, at a voltage called Vs at the surface, when the voltage at the surface here reaches a specific value, right? Okay. We'll just draw what happens to the voltage. The Vs value actually keeps increasing as we increase VGB initially. Okay. Then if you increase it even further, okay, a whole lot of electrons will now get accumulated here from the electron hole pairs that were there here. Remember this at room temperature, there's a lot of generation also happening. Right? Generation and recombination both are happening, but generation is happening, a whole electron pair were always getting formed. But the field is sufficiently high, some of these electrons which were generated by the whole electron generation gets attracted to the surface. Right? The depletion region is a little bit pushed down because the thin layer of electron now gets accumulated on the surface. When this happens, you can call it as an inversion region here. Why is it called an inversion region? You started with a p-type material in which holes were in excess, but by applying a lot of positive voltage here, you attracted the thermally generated electrons to come and sit out here. And since it is now electron rich here, okay, you actually looks like the majority carriers have flipped from the holes to the electrons. That's why it's called an inversion region. Okay. And when that happens, the voltage tends to remain constant after that. because we remember it is exponential dependence on voltage, remember? So if it is if the voltage tends to remain constant here, the field drop across this keeps increasing. And this voltage where the inversion occurs, where this electron starts to become the majority carrier, is called a threshold voltage. So beyond the threshold voltage, the voltage at this point doesn't change too much in this region, in the inversion region. Now because the voltage doesn't change, the depletion region also doesn't change too much, because depletion region depends on this potential here. So that doesn't change too much. So Q depletion remains constant. And the Q depletion is slightly below the inversion region. Now, what is the definition of our charge? Charge is nothing but, now there are two types of charges. One is the Q inversion region, which is the inversion region out here, the charge in the inversion region, plus charge in the depletion region. Because this charge hasn't vanished anywhere, it is still there. Right? And CGB, will write it as dou QGB versus dou VGB. Same, the definition remains the same. Of course, there's a negative sign which I'm forgetting right now. So CGB is the derivative of this with respect to VGB and the derivative of this with respect to VGB. But derivative of this with respect to VGB when the inversion region has occurred is 0. Because we just said that the Q depletion remains constant. Because the surface potential remains constant, the depletion region charge doesn't change with increasing VGB. So the derivative of this with respect to VGB after VTH, after Vs equal to VTH is 0. Right? So CGB is nothing but the rate of change of inversion region to VGB. And this is nothing but, again, because there's a heavy amount of charge here, is Cox. It's just Cox. It's just like a parallel plate capacitor. So you will get a, so here up to this, when the depletion region was dominating, charge was dominated by depletion region, capacitance is reducing. But once the inversion occurs, the inversion region charge is what will dominate the capacitance, hence it goes back to Cox. So this is how a capacitance between the gate and the substrate will behave. Okay. So you started with a parallel plate capacitor. This is inversion region. This is where the holes got accumulated, and this is where depletion region occurred. So CV graph, I'm just redrawing it here. So we just saw that in the inversion region, when it was done, we said the electrons were thermally generated. And we know thermal generation is a much slower process. Right? So this was the inversion region where it went to Cox. But the electrons here were attracted once they were generated by the thermal generation process. And thermal generation process is a slow process. Right? So what happens if the frequency of VGB is high? Right? Let's say it was, you bias it and then give a very high frequency. Will the electrons change? Will the charge in the inversion region, which is the electrons in this case, change as fast as VGB changes? That is not going to be true because it is limited by the number of electrons available which are thermally generated, which means it will reduce the inversion layer charge. So if you change it fast, if you change VGB fast enough, faster than what the thermal generation can accomplish, then the inversion layer charge change, right, will not follow the VGB change, which means dou inversion charge to dou VGB will be lower, which means lower CGB. So if you do a high frequency VGB, then this curve which we recovered back to Cox will not be true, but it will remain at a lower value. So the frequency VGB is high, then the capacitance doesn't recover and then remains, and unfortunately remains at the lower value itself. Okay. High frequency can be, when you talk about high frequency, it could be in few tens of kilohertz itself. Because thermal generations are of that order. Okay. Not a very good capacitor because of this limitation. Well, what is a capacitor if it's in a few megahertz? It's not acting as a capacitor. That doesn't solve my problem because most of the microelectronic circuits that we will build later will need capacitors which are good up to very high frequencies. If it's not good, then that's a problem. So we'll have to find a solution to this. Let's see what we can do. Right? But before we do that, well, we said VGB is greater than 0. We drew a thing at VGB equal to 0, but that's exactly not true. There's something called a flat band voltage, right? And that flat band voltage, the limit actually when VGB is less than V flat band voltage, it is Cox. Once it crosses flat band voltage, it follows the depletion region, and then once it hits the inversion voltage, it starts increasing back again. This flat band voltage depends on the type of semiconductor we use and the type of gate material we use. Okay. But for all practical purposes, you can assume this is the curve. Okay. If you understand where it comes from, it's good. This flat band voltage is the inbuilt potential difference between the gate material and the semiconductor material. Okay. Now we saw that the capacitor is actually not a very good cap for high frequencies in the inversion region. Right? In the accumulation region, it's still good because there's anyway holes, excessive holes, and it will be good there. Only in the inversion region, it is not very good. So let's take a look how to improve it. Right? In the inversion region, what was the problem? The problem was the slow generation of minority carriers in the bulk. Right? So bulk is not able to supply minority carriers for the inversion region. Right? So how can we solve that problem? Somewhere, if we have a source of electrons which are not the minority carrier from the bulk, that will be great. Because bulk minority carrier can be generated only by generation, which is a thermal generation, which is a slow process. Right? So we will add a source of minority carriers once the inversion sets in. And how do you do that? You just add at the two ends of this channel, just add n-type dopings. In an n-type doping, what is the majority carrier? Electrons, that's correct. So when the inversion happens, this is almost like an n-type material here. Right? So you augment it with a wantedly heavily doped n-type regions on this side. So these becomes a source of electrons. So when the inversion happens, it doesn't have to attract the electron from the bulk, but it actually can attract the electron from these reservoirs of free electrons out here. Now we got a very good capacitor because if the VGB change fast enough, you still can get free electrons from here, or you can return it back here. So this is rich in minority carriers and can supply the charges. So the capacitor now is not only across this, but you just take these two and connect it to the bulk. Remember, this is anyway a PN junction, so there is no problem here. So long as it's zero bias. If you forward biases, it's a problem. Then you'll get current from between these two terminals. That is the only thing that you need to take care. But since it's zero, it doesn't matter. You can just connect it like this. So the capacitor VGB is now between this to this inversion region, which is now connected to the external world by this n-type regions. So the resistance also is much better now. How to improve it in the accumulation region? Did it have to be improved? Remember when we said previously, the accumulation region, we had the gate type material, holes get accumulated here, and the connection actually goes through this. You see that in a moment. This is a good cap because there is enough holes out here. This is heavily doped material. So there's almost like a metal and a metal with lot of free charge carriers here. So this is still a very good cap. But from the cap bottom plate to the point where it's connected, it needs to go through the p-type material. Right? And that can have a large backside contact resistance because it has to go through the p-type material, which might not be heavily doped. If it is not heavily doped, then you get some amount of resistance from the back plate to the connection point. To improve this, we'll do the same trick as we did for the electron. Instead of a n-type material, we'll just add a p-type here. This becomes a rich source of holes, even richer than this, right? And take the connection from there. So the backside contact is not through the bulk. It is heavily, holes have become very large here, so the resistance of this plate becomes small, and it directly comes to even more heavily doped regions here which are P plus and comes out. So the resistance actually almost vanishes. Okay. So you improve the backside contact by giving an additional P plus regions out here. This works only in accumulation. In the inversion region, we have to put N plus here, N-type material. Okay. Generally, the bulk is P-type. Then this cap structure is not used as second terminal because this terminal is internally also shorted to the bulk. And that causes a lot of circuit related issues. We'll see later. So you generally don't use this kind of thing. But just to keep in mind, if you want to make something someday, you can always do that. It's an accumulation. So VGB is less than 0, but we said it's not 0, it's less than V flat band voltage. Where flat band voltage depends on this material and this material. Now we saw how to do that in P-type bulk so far. N-type bulk is the same. This is for accumulation, N-type, N plus N plus. Right. So we'll just see for various values of VGB, what is the regions of operation. So when VGB is greater than flat band voltage, when VGB is greater than the flat band voltage, it will attract a lot of electrons out here, which means it will get into accumulation region, right? Because now the electrons are the majority carrier. Right? So the majority carriers tend to accumulate in this region, which still forms a channel, but it's an accumulation because there is no the free electron free carrier type here, the same as the majority carriers in the bulk, and that's called accumulation. And when VGB is less than VTH and less than flat band, it forms a depletion region where this region is devoid of free carriers. So you get only the depletion region capacitance. And when it is less than the VTH, when VGB is less than the VTH, you attract holes. And when you attract holes, you get an inversion region here. Remember, when you attract holes, this is not a good cap because the resistance still is very large. It has to come through the the depletion region and then the N-type. So, and these are become N-type here. So that's not a good cap in the inversion region. How do you fix that? Right. So this kind of cap we'll use only in the accumulation region, because in the depletion and inversion region, the depletion region cap is small. In the inversion region, the connect to the backplate is bad. That's what we discussed right now. But how do you fix that? Instead of N-type, you put P-type here. Remember, it has to be opposite side because in the inversion region at least, this will become a P-type material at the surface. Because N-type has a majority electrons. In the inversion region, the majority here will become holes. And we'll just see the operations again. Less than VFB, it is accumulation. Nothing changes. Right? The regions of operation is exactly the same, except that the good region of operation here will be when since this is P-type, we need to have a hole here, right? And hole happens when it is in the inversion region. So that is a better region for operation for this kind of structure.